Hello everyone, in today's class we're going to go through some examples for the heat diffusion equation that we covered in the previous class. So let's go ahead and start with an example. Okay, let's assume we have a metal plate in 2 dimensions, the x-axis and the y-axis. Okay, we'll assume the thickness is L, or we'll assume it to be L, unknown, and the height to be H. Okay, the temperature in the surface of the y-axis, we'll call it T1, and the temperature at the surface of the x-axis, we'll call it T2. Okay, this is your metal plate with a constant thermal conductivity. Let's also assume that we have convection in the top. T infinity is your temperature of the surrounding, and that is your H coefficient. Okay, so let's use the heat diffusion equation for conduction that we drove in the last class to solve this example. Okay, so if I remember correctly, the heat diffusion equation is second differential of temperature over second differential of x plus second differential of temperature over second differential of y plus q dot over k equals to 1 over thermal conductivity times d temperature divided by change in time. Okay, so right off the bat we can see that there's no generation term in this example, so we can cancel this term here. There's no generation energy being generated in this example, so that could be canceled. We also notice that there's no variation with time in this problem. That means it's steady state, and this term can also be canceled. Therefore, we'll be left with change in temperature with respect to x plus change in temperature with respect to y equals 0. Okay, now to solve this equation you need at least 4 boundary conditions. 2 boundary conditions for x and 2 boundary conditions for y. Okay, so to start, before we go any further, there's one thing that I forgot to add to the example, is that the right side of the plate is perfectly insulated, meaning that there's no heat flow or heat flux in the right side, which makes it adiabatic. Okay, equals 0. Heat flux, I think flux I used Q equals 0. Okay, so that's the part that I did not add to the example. It doesn't affect the derivation here, but it does affect the boundary conditions. So we need 2 boundary conditions for the first term in terms of x, the 2 boundary conditions for the second term in terms of y. So our boundary conditions, 1, we'll say that temperature at x equals 0 at any y will equals 2. So at x equals 0, meaning here, right? And any y, no, sorry, I think I messed it up. X equals 0 is here at any y. That will be your T1. Okay, that will be your T1. and temperature at any point of x and y equals 0, that will be your, so at any point of x and y equals 0, so y equals 0 and any point of x, that'll be your T2, okay? That's your second boundary condition. Your third boundary condition is that the right side is perfectly insulated, meaning that the heat flux is 0. Okay, so we can say that negative k dt over dx at which point x equals L, at x equals L, the heat flux is 0. X equals L, your heat flux is 0. Okay. The fourth boundary condition is the heat flowing out is convection. So we'll say that the heat in the plate and the heat in the plate is, I'll write it down here. So we'll say that the conduction heat flow equals to convection heat flux, sorry, not heat flow, heat flux. So the conduction heat flux equals to the convection heat flux at point H. So we can say that conduction heat flux equals to convection heat flux, which is negative k dt over dx at y dy, sorry, dy at y equals h equals to the convection heat flux, which is h times ty, y equals h, minus T infinity, which is the temperature of the surrounding. Okay, and now using these four boundary conditions, we can solve for temperature as a function of x and y. Okay, that's the first example. For the second example, of course, you cannot get the exact value for the final answer, in a value, because we don't have the exact givens numerically. So we can only solve it so far without the exact givens, numerical givens, okay? But we'll move on to the next example, which we have the givens in terms of numerical values. So in this example, we have a wall, and it's in 1D, one-dimensional, and we have heat flowing into that wall and outside of that wall. The K value is constant for the wall. We're given the area of the wall and the thickness. Okay? We're also given the density, thermal conductivity, Cp, and energy generated per volume. We're given also the temperature distribution in the wall as a function. Yes? I'm teaching a class right now. What do you need? Sorry about that, guys. Just my sister interrupted me. But yeah, so as I was saying, we're given the temperature distribution throughout the wall as a function of x. Okay, so we're asked to find the heat flowing in and out. So we're asked to find the Q in and the Q out. Okay, we're also asked to find how much energy is being stored inside the wall. Okay, if the energy leaving is less than the energy entering, that means there's energy stored. If the energy leaving is more than the energy entering, that means there's energy being generated. Okay, so let's go ahead and solve this. So we'll start with solving for Qin. Okay, so Qin is heat flowing into the wall by conduction. So we reviewed in chapter 1 that conduction is negative Ka delta T over dx. Okay, now the Qn is at the point where x equals to 0. Okay, so your dt over dx is at point x equals 0. Now to find, your first step is to find your dt over dx at point equals 0, which is basically the differential of this equation here. The differential of that equation is negative 300 minus 100 x. Now we need to substitute x equals 0 into the equation, which will give us negative 300. Okay, we can substitute that back to the equation. Therefore, Qn will equal to negative, what is K? K is 40. The area is 10. So, negative 40 times 10 times negative 300. Therefore, Qn equals, give me a second, and that will equal 120,000 watts. Okay, now let's find Q out. Excuse me. Q out, same equation, conduction, heat transfer, negative Ka dt over dx at x equals L. L equals 1. Okay, so dt over dx at x equals 1 equals, again, the differential of this equation, which we found to be negative 300 minus 100x. Okay, we're going to substitute the value of x, which is 1, which equals negative 300 minus 100 times 1. That will be negative 400. Okay, yep, therefore Q out equals negative 40 for your K times 10 for the area times negative 400. Q out equals 160,000 watts. That is your Q in, and this is your Q out. So we notice that 120 kilowatt, 160 kilowatt. So the energy leaving is more than the energy entering. That means there's energy being generated inside this wall. Okay, so let's solve the second part of the question, which is the rate of change of energy stored in the wall, which can be solved using the material balance covered in chapter 1. Energy balance covered in chapter 1, which is energy entering minus energy leaving plus energy generated equals energy stored. Now keep in mind that in the question it states that it wants the rate of energy stored, and we figured out that energy is being generated because more energy is leaving than energy coming in. But if the question is written in a way that it's looking for the energy stored, we have to solve it that way. Yes, looking at the numbers we've got, it looks like there's no energy stored, but there is, as a matter of fact, there's energy being generated, but we're still gonna solve it depending on the question statement. So we will cancel energy being generated, write it as 0 because it's not stated in the problem statement. I know it's wrong, but we have to solve it, the problem, based on the question statement. So energy going in, we said it's 120,000 watts, which we found here. That's your energy, your heat flowing in. Okay, minus heat flowing out, which is 160,000 watts, will equal to energy stored. Therefore, energy stored is negative 40,000 watts. That right there shows you that there's no energy being stored because it's negative, where in reality it's energy generated equals 140,000 watts. That's the correct answer. Okay? That's it for this class, and see you in the next one.